Forward button. Actually, before I do that. All right, so we're still looking at integrated rate laws. Did we all have a lot of fun on Wednesday deriving those integrated rate laws? It was so much fun. Yeah, I was gonna say, be honest, because if you had a lot of fun and you really got it, I'll make you do this one on your own. The second order integrated rate law. Okay, so again, look at that rate. Tell me why it's second order. Because of the two. Always remember in science, things are super easy until they're not. Okay, so you see the rate, you see the integrated rate law. Again, remember your slope of 1 over concentration versus time. That's going to indicate that when you get a straight line for that one, that's going to indicate a second order. All right, so let's just start out. Let's take this here. We'll turn that into its differential form. And then we're going to do separation of variables. Yeah, I'll move the needle to the other side. You saw how the integral on the right works the last time, so we just know that that's going to come out to be negative KT. That's going to be the same every time. But on the left here, so we're going to get this. And this is where any of you who take calculus, this is called the power rule. And so you have a formula that solves the integral. This is why, for anyone who goes into some of the higher levels, I always suggest this nice little book called Sham's Mathematical Outlines. It's just tables. And if you can do the algebra inside the integral or the derivatives to make it look a certain way, then you can just look up the solution. All right, so if our n is a -2, this integral, so 1 over -2 plus 1, those should be primes. So now we have a -2 plus 1. All right. So this is going to be negative. And so that -1, so that's that -1 exponent means that that concentration is going to go in the denominator. Okay, we can cancel the negative out on both sides. And essentially what we're going to get now is 1 over a minus 1 over a0 equals kt. So one of the formats for this, there's not as many formats for this one because it's you don't have the logarithm. You could just leave it in the 1 over a minus 1 over a0. But these are your integrated rate laws for a second order. So then, of course, again, we have to think of the half-life of the integrated rate law. Right faster. Okay, so again, at T1 half, half of your original concentration has been used. Okay, so now if I take and I'm going to substitute in 1/2 a 0. Now what's going to happen to that 2 in the 1/2? Yep, it's going to flip and it's going to go up to the numerator. And again, the way you can think of this, let's say I have 1 over x over y. Okay, this equals y over x. That's how the fractions work. All right, so 2 minus 1, they both have the same denominator, so I can subtract those. And so then our half-life, one over K times the initial concentration of whatever your reactant A is. You're starting to get an idea of how my college life went. I did advanced math for fun and I played video games. I was Mr. Popular. So let's see if we can actually solve a problem. So here we have, so the rate law for this reaction, you can see K times the concentration of NOBR. You see it squared, so you know this is a second order reaction. If the half-life of this reaction is 2 seconds, when the original concentration of NOBR is 0.900 molar, calculate the value of the rate constant for this reaction. Does that seem fairly easy? If you got a homework problem like this, the key to solving these is going, oh, that's second order. So I can find this equation for half-life and I can solve this. Now, the thing you're going to want to pay attention to on homework problems and any problem you solve is if you're given a problem, you'll need to figure out the order of the reaction. It may tell you. So like you remember we did the one where it said, like let's say you get a problem that says a linear graph is produced by a plot of 1 over concentration versus time. If you see that, your mind should go second order. And then it will say, at what time will the concentration of the reaction decrease to this from this? Well, if I'm asked about time versus concentration, I need to use the integrated rate law. Your mind should just be working that way. The integrated rate laws are going to compare concentration to time of reaction. So any problem you see with time versus concentration, you figure out the order, grab the integrated rate law, solve it. So the half-life for this Okay. So I can multiply through, and I'll get K times the initial concentration times the half-life equals 1. And then K will equal one over all that stuff. And then I can say, well, what is K? All right, so the half-life is 2 seconds. Your value for K is going to be 0.556 liters per mole times second. Okay, now pay attention to the units again. Do you see how this value of K is different so that you're different from the first order? So for first order, K is going to have units of seconds to the -1. For this one, K has units of liters, moles -1, seconds -1. Are you seeing how the units change based off the order of the reaction? On standardized exams, you could be asked to give the order of the reaction just from the units of the K value. They're going to stay standard. So there should be a nice little table in your textbook, but you can find tables anywhere that relate the K values to their units. That's just something that will pop up on standardized exams from time to time. Or they'll give you your K for a certain reaction is this. Solve this. Well, you're supposed to look at that K value, look at the units and say, oh, this is a first order, a second order, a zero order, and solve it appropriately. Because the units on the value of K. Yep. So this one, those are the units that line up. Sometimes you'll get problems where you have to solve multiple things, like, what is this concentration at this time? Okay, well, maybe the problem didn't tell you what the value of K is. You need to figure that out first. So just kind of really make sure you're reading what's there and then say, well, I need this and this. They want me to solve this. There's 2 variables I don't have. Let's solve for the first variable I don't have and then solve for what they're actually asking for. You did that on a homework problem a couple weeks ago where you just first solve for the enthalpy of vaporization. Then you could solve the Clausius equation. Okay, so what does part B say? How much time is required for the concentration of NOBr to decrease to 0.1 molar? That right there. How much time does it take for concentration to decrease? Oh, that's an integrated rate law. So part B, I'm gonna just I'm gonna write it backwards because I'm solving for time. KT is so how much time? Well, I'm just going to do 1 over K times all of this. And so then your time is going to, so your K is your 0.556 that you just solved for. Yeah, let's use square brackets. Okay, so let's look at your concentrations that we have to put in here. It's decreasing to 0.1 molar, so that's your concentration at some time. Your initial concentration is 0.9 molar. And so then you get some fancy calculator work. The time you're solving for is going to be 16 seconds. All righty. The last one, zero order. Okay, now look at the rate. I mean, it makes sense why this is zero order. But how should I adjust that equation to make it more accurate? Rate equals what? Forget the delta in the middle. Just look at the k times a raised to the zero. Yeah, so anything to an exponent of zero is one. So your rate is k. And so then you've seen how to do this derivation twice, but so we'll just say that's your integrated rate law. Yeah. Sometimes scientists are not real inventive with their names. It sounds real fancy, integrated rate law. What is that symbol? The mathematical symbol. What is that? Okay, so what's that? That's a sum. What if I had, what is that? That's a derivative. What's that? Nope. Well, kind of, yes, actually. But what's the proper name for it? That's an integral. So not real fancy with their names. That's also why I warn people about ever going on a date with a physicist. You look up and go, that's a beautiful star. What is its name? That's XG-111A. It's so romantic, but it's so sometimes scientists are not real inventive with their names. What's really funny is eventually some physicist will see one of these videos and go, there's not a star called XG-111A. Dude, it was. That's why the Big Bang Theory is so funny. People are like, oh, they're exaggerating how a group of physicists are when they're together. No, the joke is they're not. That's the whole joke of the show. They are not exaggerating. Okay, so we have the integrated rate law. Let's think about the half-life for this. Okay, so again, we know at T1 half, your concentration of A is 1/2 the initial concentration. And so let's take the integrated rate law. Okay, so Let's turn these two concentrations into fractions that we can subtract. How do we do that? So the first one is going to be A over 2. What about that second one? They have to have the same denominator. 2A over 2. Okay, so that's going to give you we can get rid of the negative sign on both sides and solve for t. And we have the half-life for this equation, for this rate law. And we'll have to look up sometime what the units for a zero order are. But like I said, there's tables out there that will give you K and then the units based off the order of the reaction. All right, so we've been looking at reactions with with one reactant. How do we deal with reactions with two reactants? Bravo, I've taught you all you need to know. But what if I told you you had to figure out how to get to this equation? You know what's funny is the people shaking their heads at me are the ones who can probably do it. The ones who look terrified sitting in the corner going, "Don't look at me," are the ones who are going, "I don't know how to do this." And then we have some people just giving me looks like, "Can we just be done?" Huh? So now what we're going to do is we're going to use a situation where we say that E0 can someone translate this for me? What is this saying about this reaction? Not just greater than, double greater than. Is this one of those die greater than systems? No, so we write this, it's a logic symbol that means much greater than. So in chemistry, when we have one reactant that is its concentration is much greater than the other one, what do we call that? If I let this reaction run, will I notice any noticeable decrease in reactant D? No, because it's much greater than the concentration of A. So A will run out before B, you can even notice any change. And so we call this B is in what? B is in what? Very close. Yes, the chemistry word is excess. Yeah. So this is a reaction where one of your reactants is in excess. So we don't really even consider it in the in any of our rates or anything. So now that means that our rate we can just put the initial concentration of B back in because we're gonna the change in it's going to be so negligible that it's not even really going to matter. What do you mean? Not always. It's just the one we chose this time. Okay, so then what we can do is rewrite this prime. So now that K prime, so K is a constant anyway. Now that B is in excess and it's not going to have any noticeable change, it is also now a constant. So K times B initial is a new rate constant called K prime. We just subsumed both constants into a new constant. So now, this is already looking very similar to one of our integrated rate laws. What order does this look like? First order. So see what we've done here, and go to this part of the chapter and read a little bit more on it. By putting B in excess, we have created what's called a pseudo first order rate law. Okay, it's not actually first order, but we've just put one of the reactants into such an excess that we can now represent it as a first order rate law. It's called pseudo first order. So go to this part of the textbook, read a little bit more on it, make sure you're kind of grasping what they're doing. Okay, so as we go through and solve this, you notice that this left-hand side, the integral is going to give us our natural log again. Okay, so as we solve this, go back up to the first order rate law. Oh, yeah. There we go. All right, and then what we're going to do, so I'm going to go ahead and I put that there. Now, how do I get rid of natural logs? Yep, the exponential. So if I exponentiate both sides, well, the left side's easy because exponentiating a natural log, that is just going to get me my concentration back. The exponential or Euler's constant, which European names, Euler. Yeah, I know. It gave me that face the first time I saw it too. I looked at my physics professor going, how is that Euler? He's like, Europe. So then on this side, now we're going back to a little bit of algebra called how do exponentials work? How do exponents work? So you see I had the exponent of the natural log minus KT. Can I just turn that into the exponential of natural log minus the exponential of KT? No, I absolutely cannot. So what if I had x in times xy? Close. What do you do to the exponents when you multiply these two? That's the rule. So that means going backwards, I have e to the natural log of a0 times e to the minus kt. Because again, if I added those, it'd be natural log plus a minus KT, and I would just get the original exponent back. So now I'm going to have so we have our nice integrated rate law for the pseudo first order. Now, the good news is when you get assignments that have this, your calculator has that nice little E button on it. So it'll do it. And so then the half-life, oh, okay. So the half-life, we'll go ahead and put in, let's rewrite the and for those of you who ever take like the statistical thermodynamics, if you get really good at this exponential natural log calculus, that's honestly about 3/4 of the class. So you don't have to learn like all of calculus. You have to learn like the exponentials and the natural logs, and you're pretty well set. So what do we have at T1/2? Well, we're going to have 1/2 A0 equals A0 E minus KT T1/2. There we go. Or K prime. Because remember, we have that B0 subsumed into the K value. So if I divide through by A0, that's going to cancel those two out, which is going to give me I skipped a step. Let me not do that to you. Okay, so 1/2 now I'll do the natural log. Now, if I exponentiate a natural log and get the what's inside the natural log back, what happens when I natural log an exponential? Yeah, so the natural log will get rid of the exponential, and that's just going to give me minus A prime. Now, do you remember in the first order half-life, what was natural log of 2? No calculators. What is the natural log? 1/2. It's what? It is, no, not inverse. If I have a number that's less than 1 inside of a logarithm, what? Negative. So we end up pretty much at the same place, as we would expect, since we modeled this as a pseudo first order. We just have to remember that in the pseudo first order regime, we have this initial concentration of reactant B. All right, so that is integrated rate laws. Now we'll start something that should be a little more straightforward for you. Let's talk about reaction mechanisms. A reaction mechanism is essentially, you see you have your overall reaction at the top. That's the reaction you're looking for. In industry and other places, most of these reactions happen in steps. So down at the bottom, you see a two-step process that creates the reaction at the top. That two-step process at the bottom is called the reaction mechanism. And so each one of them is going to have their own individual rate constant. So now it'll start making more sense when we draw the double arrows. So you see like a K1 and K minus 1. So the K1 is the forward reaction, the K minus 1 is the reverse reaction. And now K1 and K minus 1 do not necessarily equal K. Intermediates, that's a fun thing. So when you remember when you add together chemical equations, which is what you're going to do to, like, remember you add, you get the overall reaction, you cross out compounds that are the same on both sides of the arrow, but only some of those compounds are intermediates. So if you add these two together, you see I have NO2 here and NO2 there. When I add those together, NO2 is going to cancel out because it's the same on both sides of the arrow sum. However, NO2 is not an intermediate. That reaction mechanism, what's the intermediate? NO3, because intermediates have to be created and then used during the process. You notice that NO3 is not one of the original reactants. Yeah, pretty much, yeah. Yeah, same concept. So yeah, if you add these two together, you just write down everything with the reactant and everything with the product, then you cancel out what's the same on both sides, you should get the overall reaction back. It's just you have to be careful when you're calling certain things intermediates. An intermediate is created during the process and then completely used during the process. In this case, only NO3 fits that. Does it have to be completely used or can it make sense? There can be excess, but in time being, we're just going to say completely used because it's saying more straightforward. But if you were working in industry, yeah, you're going to have residues that you're going to have to dispose of. Now, a lot of times you can just leave them in the reaction, and some of them will get used. But yeah, in reality, some of the intermediates you may have nothing. They just have to be a compound that's created during the process and then used for another part of the process. Okay. Now, in a reaction mechanism, each step represents an elementary reaction. An elementary reaction is a chemical reaction that takes place with a single collision of the reactant molecule. Now, the rate law of elementary reactions can be written using the stoichiometry of the reaction itself. But you can only do this with elementary reactions. So, like for your first one here, you see how I use the stoichiometric coefficient as the exponent? That can only happen for an elementary reaction. So for your second one here, now we will get to, we are going to be judging reaction mechanisms. So if we're doing that, let's go ahead and see we remind ourselves what it looks like to add together chemical equations. So if I add these, so what I'm going to get is 2 NOs plus nitrogen peroxide. Okay. And then what's the same on both sides is going to be the N2O2. So it cancels. And we get, well, am I missing something?
Is there any difference?
No, I'm not. Not really, no. We're not going to do that at this level because that's going to involve some other stuff that's going on. So yeah, if you have like N2O2 in solution and N2O2 in gas phase, they're really not going to cancel each other out. So we're just going to leave that alone for the time being. And you'll do stuff like that as you get into like your 300 and 400 level chemistries. Okay. So that's how we do the overall reaction. Now, reactions can have different molecularity. They can be unimolecular, bimolecular, termolecular. Look at these intermediate steps up there. What are they? Which one? The second one is the one. Why is that first one bimolecular? Yep, you have 2 NOs widened to get the process done. So make sure you're reading your equation, your chemical equation all the way through. The second one bimolecular, so I just have one of them. Look at the coefficients in front.